Okay, welcome to Unit 3, Lesson 6. So thus far this unit we've explored functions and function notation, linear models, quadratic models, and now today we're going to move on to exponential functions. So exponential functions are a new type of function for you, and the goals here are to identify and represent exponential functions and their graphs, and to show an understanding of the equation of a horizontal asymptote. So in order to accomplish these goals, we first need to understand the properties of exponential functions. So there are some unique characteristics of exponential functions that we will take a look at right now. So one of the things that makes exponential functions different is that the independent variable is the exponent. So usually we're accustomed to putting an exponent on the variable, but this time the variable is the exponent. So here are some examples of what that looks like. So in all cases, you can see that x is actually an exponent in these functions. So if we think about sort of the parent function or the main exponential function, there are two different types: increasing exponential functions and decreasing exponential functions. So we'll take a look at each of these individually. So increasing exponential functions have an equation that looks like f of x equals some number a to the exponent x, where a is not equal to 1. And that's because if a were 1, it would just always be 1. 1 to any exponent will still be 1. So here are some examples of some graphs of increasing exponential functions. So this one is 4 to the power of x, and this one is 5 to the power of x. So a couple of things you'll notice is that the y values increase as the x values increase. So we get this increasing pattern on the graph where we start small and we increase with larger x values, and that's exhibited in both of these graphs here. Now what's interesting about exponential functions is when the value of x gets really large, the values of y get even larger, because as the exponent gets very large, the value itself will get very large. And in fact, it'll get to the point where the y value, or the f of x value, approaches infinity. So it will get infinitely large as the x values get larger. As something quite the opposite happens as the x values get smaller. So if you look to the left end of these graphs up here, as the x values get smaller, we have this sort of flattening appearance of the graph. So it basically gets closer and closer to a horizontal line and closer and closer to the x-axis. So this is called the horizontal asymptote. So we're reaching a point where it's getting almost horizontal. And in this case, the horizontal asymptote is y equals 0. So this is like an imaginary horizontal line that the graph will approach but never actually reach. So it'll get really, really close, but it'll never actually reach that horizontal asymptote. So it'll come down and it'll get very close but never actually cross, and it'll just continue like that for all values of x. And that's because if we have a function, say for example f of x equals 4 to the x, there's no value of x that can make this entire thing equal 0. Even if x is very, very small, there will still be a y value. It will just be very, very small. It will never actually equal 0, which is what causes this asymptotic behavior. So if you look at both of these graphs, they all pass through the point 0, 1, which is the y-intercept, and they all have the equation y equals 0 as a horizontal asymptote. So when you're in this form, f of x equals a to the x, two things will always be true. The y-intercept will always be 1, and the horizontal asymptote will always be y equals 0. So if we consider our domain here, our domain is just going to be all x values, all real numbers, because we can extend horizontally in any direction. Now for our range, we have to consider the asymptotic behavior. So our range will be real numbers, but y has to be greater than 0. And it can't be greater than or equal to, because as we talked about over here, y will never equal 0. So it can be greater than 0, but never actually equal to. So decreasing functions, decreasing exponential functions are quite similar. So in these ones, they still have the format of f of x equals a to the x, but here a is going to be between 0 and 1. So a will be a fraction, and that's what causes the switch to a decreasing behavior. So it's just kind of the same thing as before, but in reverse. So here, the y values will decrease as the x values increase from left to right, and that's what causes this downwards pattern. Sometimes this is called exponential decay. We still see asymptotic behavior though. So as the values of x get larger, the curve approaches a horizontal asymptote for the same reason. So in something like this example, which is 1/2 to the power of x, we can never, no value of x will ever make this equal to 0. So we still see this asymptotic behavior approaching the x-axis. So this graph also passes through the point 0, 1, and that's because if we substitute in 0 for x, anything to the power of 0 is 1. And it's similar for the increasing exponential functions. When x is 0, y will be 1, so you'll always have a y-intercept of 1. And it also has the equation y equals 0 as a horizontal asymptote. Our domain and range manifest in the same way as increasing exponential functions. So our domain is all real numbers for the x's, and our range is real numbers such that those real numbers are greater than 0, because y can never equal 0 and it will never go below 0. So these are kind of the parent functions for exponentials. And this is, again, when the format of the function is f of x equals a to the x. Now, there can be levels of complexity added onto this. So that's what we're going to look at next. So here are a couple of examples where the format of the equation gets a little more complex. So in these equations, we have something that looks like some number k multiplied by a to the x. So now we have a coefficient in front of the exponential term. And on the right, we have functions that have the coefficient as well as a constant at the end. So f of x equals k times a to the x plus c. So we'll look at what distinguishes or what's interesting about these two types. So let's start with the coefficient only. And there are some examples given here. 2 times 3 to the x, that's the one we'll start with. So the first step is to graph this function. So we're going to have 2 times 3 to the power of x. And then when we graph that function, we should see an increasing exponential function because our base is bigger than 1. So again, we see this pattern that looks very exponential, and we can write down some information about it. So the value of k in this equation is the coefficient. So here k equals 2. The y-axis point, or the y-intercept, we can figure out a couple of ways. We can substitute in x equals 0, and then we'll get 2 times 3 to the 0, which is 2 times 1, which is 2. We can also do this on the calculator with a second trace value when x equals 0, and we should see that y equals 2. So the point where the graph crosses the y-axis is 0, 2. The equation of the horizontal asymptote, we can see that it's approaching the x-axis. It kind of looks like it touches. If we were to zoom in, we would see that it actually doesn't. Another option for identifying the asymptote is to look at the table. So if you go to second table, you can see that as our x values get smaller, our y values get smaller, but our y values will never actually equal 0. They'll get really close, but they won't actually get there. See, this scientific notation means the y values are getting smaller and smaller. So our horizontal asymptote is the line that approaches y equals 0. And then our domain and range, we have a domain of x is an element of the real numbers, and we have a range where y can be any real number, but it has to be greater than 0. So similar to the other functions we saw earlier, so greater than 0. So that's for the example of 2 times 3 to the power of x. So let's do one more example where we look at the third one, negative 3 times 2 to the power of x. So here, our k value is negative 3. That's our coefficient. Our y-intercept is going to be the same. So again, if we sub in x equals 0, we'll get negative 3 times 2 to the power of x, which is negative 3 times 1, which is negative 3. So a pattern is emerging where the y-intercept in these functions is equal to k. So that's a really key thing to note about exponential functions that have a coefficient of k. If we were to graph this one, so negative 3 times 2 to the power of x, we would see similar asymptotic behavior. So the asymptote again is approaching y equals 0. It's just this time, because our k value is negative, our graph is reflected in the x-axis, but the asymptotic behavior is the same. Now, the reflection causes a slight difference in our range. So our domain will still be all real numbers. Our range is now going to be y values that are less than 0, because we're going to have all negative y values because of that negative coefficient. So you can see that the k value always corresponds to the y-intercept in these instances. So that's kind of a handy thing to know. Now let's look over at the ones that have both the coefficient and a constant. So we'll look at the first example, which is 2 to the power of x plus 3. And we'll write down some key things about this graph. So in this example, k is 1. It's really tempting to think that k is 2, but k isn't the base, k is the coefficient. So if you imagine a coefficient in front of the 2 here, it would be a 1. And c is equal to 3. The point where the graph crosses the y-axis gets a little bit different in these examples. So if we look at the graph, we can see that it crosses the y-axis at 4. Looks like it happens at y equals 4 here. We can confirm that with a second trace value at x equals 0, y equals 4. And algebraically, we see that when we substitute in x equals 0, we get 1 plus 3, which is 4. So our y-intercept is at 0, 4. The horizontal asymptote, you'll notice, has also changed. It's like we've shifted the whole graph up. So you can see the horizontal asymptote here. It comes down below 4, and the horizontal asymptote appears to be around y equals 3. But we can also look at our table and see that as our x values get lower, we get closer and closer to 3. These aren't actually equal to 3, it's just because the calculator can't display enough decimal places. So our asymptote now occurs at y equals 3. You always need to communicate the asymptote as an equation with y equals and the number, because it's meant to reflect linear behavior. So you have to express it like a line, y equals 3. And the domain and range, if we look back at our graph, we have a domain of all the real numbers, and now we have a range. Again, the range is always dependent on the asymptote. So we have a range where y will always have to be larger than 3. So it will never equal 3 and it will never go below 3. So this is what we see for the first example here. And let's do the third example as well. So negative 2 times 3 to the power of x plus 5. So if we work with this on our calculator, so we have negative 2 times 3 to the power of x, and then plus 5. So if we look at this graph, we see a couple of things happening. The negative coefficient is causing that reflective behavior we saw earlier, and the c value is kind of shifting things around. So if we look at this example, we have a k value of -2 and a c value of 5. Our y-intercept appears to be at 3. And if we just double check this, we get y equals 3. And again, algebraically, we would get -2 times 3 to the power of 0 plus 5. And so when we simplify that, we get -2 times 1 plus 5, and -2 plus 5 is 3. So that's why that makes sense. Our asymptotic behavior appears to come up above 3. Looks like it's around 5. And again, if we look at the table, we can confirm that we're getting closer and closer to 5 without actually equaling it. Again, this is a display issue on the calculator because of the number of decimal places. So our asymptote is at y equals 5. And again, our domain is always going to be all of the real numbers, and our range will be dictated by that asymptote. So y will always be less than 5. So this is what we see for this second function here. So a couple of things emerge from these patterns. So here we see that the y-intercept always seems to be equal to the coefficient plus the constant. So 1 plus 3 gives us 4. -2 plus 5 gives us 3. So our y-intercept is always going to be k plus c. And our asymptote always seems to be at y equals c. And that's true for everything. So here when c was 0 and it didn't manifest in the equation, our asymptote is 0. C is 3, y equals 3. C is 5, y equals 5. So we can identify some of the key features just from the equation without even having to graph it, but it's also nice to be able to graph it on the GDC and confirm those features are correct. So a kind of summary we end up having is that when we have a graph of k times a to the x plus c, y equals c is the horizontal asymptote, and the y-intercept is 0, k plus c. So you can see that here when we have an asymptote around y equals 1, which is the c value, and our intercept is 0, 4, which is 3 plus 1. If the exponent is negative, things are generally the same. Nothing changes about the horizontal asymptote. Nothing changes about the y-intercept. The only difference is that it's reflected in the y-axis. So it just switches from left to right. But the rules about the horizontal asymptote and the y-intercept remain the same. So we'll try one example just to summarize these kinds of things. So we have two functions given. We have an exponential function and we have a quadratic function. So the first question is the equation of the horizontal asymptote for f of x. And we remember that the horizontal asymptote is always at the c value. So that's going to be y equals -2. And you really need to write it with both the y and the number as well. The coordinates of the point of intersection of the two graphs. So in order to do that, you need to use your GDC and you need to show a sketch of that solution. So we're going to go to our GDC. We're going to enter both equations. So 0.5 to the power of x, subtract 2, and negative x squared plus 4. And when we graph both of those, we're going to see one exponential function and one parabola. So our exponential function comes down like this, and our parabola seems to come up for the first point of intersection in the top left quadrant and then down like that. And we're going to look for the 2 points of intersection. And it wants coordinates, so we're going to give both x and y. So when I do my intersection, I'm going to trace over to the leftmost point of intersection first. I'm going to press enter 3 times, and I'm going to get coordinates, if I round to 3 sig figs, negative 1.67 and 1.19 for the first one. And then when I do this again, and I trace over closer to the second point of intersection, I'm going to get coordinates of 2.41 and negative 1.81. So those are my points of intersection. I've supported that work with a graph of the two functions. And then it's asking me to make sort of a nicer sketch, and it's specifying a domain for me here. A good way to be able to sketch accurately within that domain is to match your window to the domain. So I'm going to change my window from -3 to 3 on the x's because that's what I was given in the question. And then I can really just sketch exactly what I see. So if this is -3 and this is 3, what I appear to have is something that kind of looks like this, and another thing that kind of looks like this. And so that's a way you can sketch the graphs that match the domain, and you can identify your points of intersection. And you can label them on the graph just to be detailed. Now, the last question is asking for the set of values where f of x is less than g of x. So f of x is our exponential and g of x is our quadratic. So it basically wants to know when is the exponential curve below or less than the quadratic curve. So if we look at our graph visually, we see that that happens between the points of intersection. So starting at this point of intersection, they cross over. F of x is the lower graph for that area. Now, at the points of intersection, they're equal. And we weren't asked for when f of x is less than or equal to g of x, just less than. So when we're reflecting our set of x values, it's going to be from negative 1.67. X is greater than that, so not including that one because we don't want equal to, and less than 2.41. And you express this group of values as a set. So this statement will be true for all x values bigger than negative 1.67 and smaller than 2.41. So that reviews the features of exponential functions and how you can approach problems involving those types of functions.